Ever wonder how an AI can master a game it's never seen before? I mean, how does it go from knowing absolutely nothing to playing like a pro? Well, that's the whole idea behind Q-learning, one of the most powerful concepts in artificial intelligence. Today, we're going to break down exactly how it works. So let's start with that central puzzle, right? Picture a robot dropped into a maze. It has no map, no instructions, nothing. How does it go from just bumping into walls to finding the fastest way out? This is the exact problem Q-learning was designed to solve. To really get this, let's turn it into a story. Think of our AI as a hero on a quest. It's taking its very first steps into a totally unknown world, but it has a goal. Now, every good story needs a hero. In the world of AI, we call our hero the agent. This is our decision maker. It could be a character in a game, a robot, you name it. It's the one that's going to explore and learn from what happens. And of course, every hero needs a world to explore. We call this the environment. This could be anything really, a video game level, a chessboard, even the stock market. The environment is basically the sandbox our agent gets to play in. It sets the rules. Okay, so at any given moment, our hero is in what we call a state. That's just a fancy way of saying its current position or situation. And from that state, it has a bunch of possible actions it can take. It's kind of like the agent is constantly asking itself two questions. All right, where am I right now? And, okay, what can I do from here? So how does our hero know if it's doing the right thing? That's where rewards come in. A reward is just a score. The environment gives it a +1 for getting closer to the goal, or a -1 for, falling into a pit. This super simple feedback is the only guide our agent has on its entire journey. All right, so our hero can move around, and it gets these little scores. But how does it remember what it's learned? It can't just wander around forever. It needs a guide, and that's where it starts to build its very own internal treasure map. This map is called the Q table, and it is the absolute heart of this whole process. Think of it like a giant spreadsheet or cheat sheet. The rows are every single place our hero could possibly be, every state. And the columns? That's every single move it could make from that spot, every action. And here is the most important part. When our hero starts out, this entire table is filled with zeros, just all zeros. This represents complete ignorance. The agent has no clue if moving left from position A is good, bad, or indifferent. It starts as a total blank slip. Each number in this table is what we call a Q value. And listen, this is key. A Q value isn't just about the immediate reward. It's the agent's best guess about the total future reward it's going to get if it makes that move. It's a measure of the long-term quality of an action. And yep, that's where the Q in Q-learning comes from. So you're probably wondering, how does this blank map get filled in? Well, it learns through pure trial and error. It's all about a series of aha moments where it suddenly realizes, whoa, okay, that path is way better than the other one. Now, this whole process of updating the map has a kind of technical name, temporal-difference learning. I know, it sounds super complicated, but the idea is actually really simple. Temporal just means over time. The agent learns from the difference between what it thought was going to happen and what actually happened. That little moment of surprise, that's everything. It all comes down to this simple but incredibly powerful 4-step loop. Step 1, the agent makes a move. Step 2, it sees what happens, gets a reward, ends up in a new spot. Step 3, it calculates that surprise factor. And finally, step 4, it updates its map with this new insight. Then it just does this again and again and again, thousands, sometimes millions of times. And with every single cycle, that map gets a little bit smarter. The logic behind this update is all about thinking ahead. The value of any square on this map isn't just the prize you get right then. No, it's that immediate prize plus the value of the best move you can make from your new spot. This is what forces the agent to learn how to play the long game, not just chase after quick wins. Okay, but as our hero's map starts to get filled in, it faces a really big choice at every single turn. And this dilemma, well, it's one of the most important ideas in all of this. It's the classic dilemma, exploration versus exploitation. Should the agent exploit its knowledge by following what it thinks is the best path on its map, or should it explore by trying a totally random move, just in case there's a secret, even better path it doesn't know about yet? It's this constant trade-off between cashing in on what you know versus investing in finding out more. So how do you solve this? I mean, you don't want the agent just getting stuck doing the same thing over and over, but you also don't want it wandering randomly forever. The solution is this really simple but brilliant balancing act called epsilon greedy. Here's how it works. It's great. Most of the time, let's say 90% of the time, the agent is greedy. It exploits what it knows. It follows the map. But that other 10% of the time, that's the epsilon. It does something completely random. It explores. And that tiny chance of just trying something new ensures it never stops learning and can always stumble upon even better ways of doing things.
Now, this whole Q table, this map idea, it's fantastic, as long as the world is pretty small. But what happens when the world gets so huge you could never possibly draw a big enough map? Well, in this last part, we're going to see how this idea evolves from a simple table into something more like an artificial mind.
I mean, think about a game like chess or Go. The number of possible board positions, it's literally larger than the number of atoms in the known universe. You could never build a Q table for that. The map would be impossibly huge. So what do? The answer is we stop giving our hero a map and instead we give it a brain. This is the incredible leap to what we call deep Q networks, or DQNs. Instead of a giant table that has to memorize the value of every single state, we use a neural network that learns the patterns of the game. It can look at a situation it has never ever seen before and still estimate how good a move is, kind of like how a human grandmaster uses intuition. It learns to generalize instead of just memorizing. And this is where it all comes together. This amazing combination of Q-learning's simple feedback loop with the generalization power of a neural network. Well, that's the magic behind some of modern AI's biggest breakthroughs. We're talking about everything from beating the world's best Go players to controlling robotic arms with incredible precision and even helping to discover new medicines. The impact is just enormous. So let's end with this thought. We started with a simple hero in a maze, just learning to fill out a treasure map. But that very same fundamental process, trial, error, surprise, and updating what you know, is now being used to tackle some of the most complex challenges we face. It really just leaves you with one question. What's the next great challenge an AI agent is going to master for us?